Okay, we're on the third part of chapter 10 on projectile and satellite motion, and we're going to discuss elliptical orbits. So I'm going to dismiss um, my image here, and we'll start the discussion on elliptical orbits. A projectile just above the atmosphere will follow an elliptical path if given a horizontal speed greater than 8 kilometers per second. Uh, the generic orbital path is an ellipse. As a matter of fact, all of the planets that circle the sun have elliptical orbits. Some are more elliptical than others. The eccentricity determines how much of an ellipse it is. If a orbit has a very low eccentricity, then it's almost circular. If it has a very, some of the comets have a very, very high eccentricity. They're very, very elongated. Most of the, well, we'll discuss Kepler in a little bit. Kepler was the one that discovered that they were elliptical orbits. So an ellipse is a special kind of oval. It can be formed by attaching a loop of string to two pins, the foci, and tracing with a marker. A circle is a special case of an ellipse with coincident foci. So if you bring the foci together so that it's really one focus, then you get a circle. Let's see. The speed of orbiting satellite varies. If initial speed exceeds that needed for a circular orbit, that is 8 kilometers per second, the satellite overshoots the circular path and moves away from the Earth. The satellite loses speed as it gets further and then regains speed as it falls back toward the Earth. It rejoins its original path with the same speed it had initially. Procedure is repeated. Now, think about when you throw a ball up in the air. Let's say you throw it at 3 meters per second up into the air. At 2 meters, after a second, it's slowed down to 2 meters per second. After 2 seconds, it's slowed down to 1 meter per second. And after 3 seconds, it's at 0. And then it returns to Earth at 1 meter per second after another second, 2 meters per second after another, and 3 meters per second after a third. This is after it reaches its peak. Well, the same thing is happening in an elliptical orbit. As this thing goes, it's almost like throwing a ball up, and it reaches its peak, and then it comes back down. But it's not coming back down to the Earth. It's making an orbit, and we'll see how that plays in Kepler's laws. Okay, the speed of a satellite in an elliptical orbit is greatest when farthest from the Earth, is least when farthest from the Earth, remains constant for all elliptical orbits, or is greatest if the orbit is circular. Well, the greatest is when the speed is greatest when it's closest to the Earth, so it's least when it's farthest from the Earth. B. A satellite in an elliptical orbit half the time recedes from Earth and loses speed, and half the time approaches Earth and gains speed. So just like I was talking about, throwing a ball up in the air and it reaches zero velocity, zero vertical velocity at its apex. So a satellite is the slowest when it's farthest from the Earth, and it's fastest when it's closest to the Earth. Oh, and that's the end of part 3. Just a little bit on circular orbits. I probably should have included that with part 2, but it's okay. We'll just stop it here.